Good afternoon, class. Today we're going to look at solving rational and radical equations. I need to do some writing first. So let's start off. A rational number is any number that can be written as one integer over another integer. In other words, a fraction. So a rational equation is any equation that contains fractions. We saw an equation with fractions at the end of the last class, but what's different here is that these denominators will have variables in them as well. That one that we did the last time at the end of class, remember we just had denominators of numbers, okay? The constants were in the denominator. Here we'll have, I'll say, any equation containing fractions. Make a note that in this case we're going to have variables in the denominator. So I'll make a little parenthetical note right here. There'll be variables in denominators. We're going to start off with an equation that contains fractions. Then we're going to wind up solving an equation that doesn't contain fractions. We're going to pull that trick of multiplying through by whatever it takes to cancel out every denominator.
Like over here, it was what number?
Over here we had to multiply through by 14. That was the smallest number, the least common denominator that we could have used to cancel the 2 and the 14. Could have used 24, could have used 50.
No, could have used 28.
I mean 28, you could have used 56.
You couldn't have used 24. Because it would have canceled out the 14.
The problem is that when we solve the equation, we're going to start off with fractions. We're going to end up solving something that doesn't have a fraction. And so the answer we get may be an unacceptable solution, unfortunately, because fractions are not always defined. When is a fraction undefined? When is a fraction undefined? A number divided by 0. Suppose you have a number divided by 0, NO. What does that say? No, you cannot do it. Fractions are undefined when their denominator is 0. And if you think about why, if you think of that division algorithm, the reason behind that is obvious. Think about, what do you learn first? When you were in elementary school and you were learning arithmetic, what did you learn first? Multiplication or division? Multiplication, because division is defined in terms of multiplication. We say 10 divided by 2 is equal to 5. Why? Because 5 times 2 gives you 10. 5 times 2 gives you 10. The value of a fraction is the number that you multiply the denominator by to give you that number up there. Suppose we had something like 7 divided by 0. What number times 0 will give you 7? Nothing. That's right, nothing. That's why we say that division is undefined. So when we're solving equations with fractions that have variables in the denominators, we're going to have to make sure that we verify that the solutions we get don't give us denominators of 0 in the original problem. The first couple of problems in this assignment are just asking you what numbers could not possibly be solutions. In other words, they want to know when are the fractions that appear undefined. Let's look at number 1.
Oh, by the way, sometimes students say 0 over 0.
0 over 0 is also, you say, well, that equals 0.
Or
no,
1. No.
It could equal 1. It could equal 50 million. Division has to be unique. look at 0 over 0. What one number times 0 will give you a 0? It's not just one number, it's any number. So even if the numerator is 0, we say the division is undefined because we don't want a quotient that can be any number in the world. This quotient of a division problem has to be unique. For example, 10 divided by 2 is equal to 5. Is there anything other than 5? Maybe 7 would work. Is 10 divided by 2 also 7? No, the only solution is 5. But for our purposes, just remember, when a denominator is 0, the fraction is undefined. Looking at number 1, all they want to know, what values of the variable cannot possibly be solutions for the given equation without actually solving the equation. They just want to know what numbers would be unacceptable solutions. Let me write the problem down. 7 over 4x plus 3 minus 1 over x minus 5 is equal to 0.
That could have asked, when are these fractions undefined, and you'd be doing the same thing.
The numbers that cannot possibly be solutions are the numbers that make the fractions undefined. So, when is this first fraction undefined? We don't want that denominator, that first denominator, we don't want it to be 0. I'm going to write it as 4x plus 3 can't be 0. And I'll use that little not equal to symbol as if it were just an equal sign, okay? What will I do first to solve this equation? Or inequality, whatever you want to call
How
it.
do we isolate that x?
What do we do first? We need to get x by itself. Okay, so we're moving the 3 over. That says 4x is equal to negative 3. Cannot equal negative 3. And then what do we do? Divide by 4, and that gives us that x cannot equal negative 3/4. So there's one of the numbers that can't possibly be a solution. If you went through and solved that equation and you got negative 3/4 at the end, you'd have to cross it out. The second denominator, we can't let that second denominator be 0, so x minus 5 can't equal 0. Oh, this is easier. That means x cannot equal what? 5. So we have two solutions. Two answers we're typing in. You can't plug in a negative 3/4 for x, and you can't plug in a positive 5. For the first couple of problems, all they're asking you to do is decide when the fractions are undefined. If you went through and you solved that equation and you got 5 at the end, you'd have to cross it out. Typing in the answers, negative 3/4.
Can I move this up?
Yeah, move it up. Okay, there.
Okay, so negative 3 over 4.
Don't put the comma in the denominator.
Sometimes
Do
I
the
get
right
students
arrow
for this
out.
problem, they'll send me screenshots. They typed the right answer and it said wrong. And send me screenshots. I'm like, no, that's not the right answer. Do y'all see what's wrong there? That comma
Correct.
5 should not be in the bottom of a fraction. It doesn't know what I did wrong. It just knows that's not right. So let me come over here. Now, negative 3 over 5.
Do the right arrow.
Comma, 5. Check answer. Okay? Now, before we do the next question, I want to show y'all something. Like, here's a problem 4, which says solve. This one we're actually going to solve, but notice, there's this option B. It's possible you'll go through and get numbers.
What number would make those fractions undefined? That doesn't take too much effort. 4, if you went through and you solved that equation and got 4, you'd have to cross out that answer and then select the option, the solution is the empty set. Now, if you get x equals 4 as your answer and nothing else, then 4 is unacceptable. So as we go through solving the things, the last step, we're going to have to make sure that any solution we get doesn't give us a denominator of 0. So go into number 2.
Oh, this has 3 fractions. 2 of them are pretty easy to figure out when they're undefined. The first one and the second one?
1 over x plus 2.
Minus 2.
Minus 2?
Mm-hmm.
X. 1 over x minus 2 plus 1 over x plus 4 is equal to 1 over x plus 2x, x squared plus 2x minus 8. Let me look and make sure I didn't miscopy this. X minus 2, x plus 4. Let's look back over here at the number 1 that I just did. Before we go on, suppose the problem had said had a 7x up on top there, and instead of a 1, that had been a 13. Would that change any of our answers? Would that change the work here? A fraction, does the value of the numerator matter? No, it's the value of the denominator that decides whether the thing is defined or undefined. You could have anything you want to up there in the numerator that doesn't affect the numbers that make the fractions undefined. To determine when they're undefined, you're only using the denominators. Okay, so I have this problem here. Suppose I'd, instead of a 1 there, suppose I'd had a 15. Would that change anything? No, the only thing that matters is when are the denominators equal to 0. You don't want x minus 2 to equal 0. You don't want x plus 4 to equal 0. And you don't want that messy third denominator, x squared plus 2x minus 8, to equal 0. Solving the first one, this is fast. What are we going to get? Okay, moving that minus 2 over, we get x can't equal a positive 2. So there's one of my solutions. We can't plug in a 2 or else we'll get a denominator of 0. What about the next one? Okay, moving the 4 over, we get x does not equal negative 4. Oh, those linear denominators are nice. Unfortunately, this is quadratic. We're going to have to use one of those methods we saw the last time. We could use the quadratic formula. It's not set up for the square root method. I think it's factorable. This is a good chance for us to practice our factoring skills. I'm going to write my 2 sets of parentheses. Doesn't equal 0. Oh, my 0 is cut off there. There.
That made it better.
It did. I think that's better. Okay. X squared, there's only one possibility. What is it? 1 times 1, so 1x times 1x. What do we know about the signs? The last one's a minus, so one's positive and one's negative. I'll go ahead and write it in there. And then what times what gives us 8? It's either 1 times 8 or 2 times 4. This is a simple trinomial. That leading coefficient is a 1. So you choose the pair that adds or subtracts to give you that number right there. I think one of these pairs subtracts to give me a 2. Which one is it?
4 and 2.
4 and 2, you want a positive 2, so the plus goes to the bigger number. So plus 4, look at that, all that effort. Are we going to get any new numbers to discard? X plus 4, haven't we already set that not equal to 0? X minus 2, we've already set that not equal to 0. You ask, well, how often does that happen where the quadratic denominator is factored using the linear factors? I'll tell you this, more often than you'd think, okay? This does happen, especially in the area of applications, and I'm thinking of rate and time, okay? So, but there's no need to set these things not equal to 0. We've already picked up our two solutions, 2 and negative 4. Any questions there? When asked what numbers can't be solutions and you're not solving, all you're doing is asking yourself, when is the denominator equal to 0? And the numerators themselves don't matter for something like this. Now, to solve a rational equation, we're going to use that same process we used for that last problem on Monday. Oh, is today Wednesday or Monday?
Today's Wednesday.
Oh, it's Wednesday. Okay.
Yeah, you were right.
Okay.
You said we were using the same process as Monday.
Okay. So they remember it hasn't been 5 days since we had class. Okay. To solve a rational equation, I'm just going to write a general process. I said the last time that denominator you're multiplying through by is called the least common denominator. And in this case, we're going to have some variables appearing in the least common denominator. The first step, we'll have to multiply both sides by the least common denominator. And I'm going to make a note here that you're going to have to distribute. Remember, what it looks like is you're multiplying every term by that least common denominator. Remember the way he said he found the least common denominator and he put it out there beside each term. That's what we're going to be doing here. And so I'm going to make a note here. In this first step, distribute, D-I-S. Oh, goodness. D-I-S-T. I wrote D-E though, distribute, yeah. So we're gonna have to remember we're distributing here. The second step.
The first thing to do.
Oh, I can assure you it is. The next thing we're gonna do, you're gonna cross cancel to get rid of all the fractions. Cross cancel to eliminate fractions. Then the third step. At this point, you're going to have an equation that doesn't have any fractions. So you'll have to solve the equation. The equation will not have any fractions now because you've canceled them out. Fourth and final step. You're going to have to make sure that the numbers that you found don't produce a denominator of 0. I think I'll say it like this. Cross out any solution that gives a denominator of 0. And with that in mind, we can't just keep having the problems, what numbers can't be solutions. We're going to have to start solving these things. So let's look at number 4.
Everyone got credit for problem 3.
Mm-hmm.
which oddly enough was the hardest problem in the assignment.
No, number 9.
Number 9? Okay.
Yeah. Mm-hmm.
Then the second hardest.
Okay,
problem.
that's
Okay.
right. Okay, so you know what? I guess that's our great weakness, Tony. We just have too much compassion. Removing the two hardest problems from the assignment. Too much compassion, I say. X over x minus 4 is equal to, the bad thing is I don't remember what movie the line that came from,
some movie
okay?
where the person-
It's equal to 4 over x minus 4 and a plus 5.
Now, he was spreading it out
Notice how I spread this stuff out.
like I did on that like problem 15.
I didn't spread it out enough though. I should have left a little more space right here. Okay, if you have the same denominator being repeated, what's the least common denominator? What do you want to cancel out? In this fraction, what do you want to cancel out? Should be obvious. You want to cancel out the denominator, which is x minus 4. What do you want to cancel out of the second fraction?
X minus 4.
There's nothing here to cancel out in the third term, but you still have to multiply. You're going to distribute that denominator across both sides. If you have the same denominator appearing, then the least common denominator is just the denominator that appears. We're going to multiply by, LCD stands for least common denominator. We're going to multiply by x minus 4. Multiply by x minus 4. Multiply by x minus 4. Here I'm multiplying by x minus 4. And I'm going to put it over 1. That just looks better. Here I'm going to multiply. This is where I said I didn't leave enough room. I'm going to put it x minus 4 over 1. Can y'all read what I've written there?
It's messy,
Yeah, it's messy.
but nothing compared to number 3.
Yeah. Mhm. Looking at the first product. Looking at the first product. What's about to cancel out? The x minus 4s. So what are we going to have left? I can't hear y'all. We have a 1 in the bottom, but we have something else still up on top. The x over
someone say
1
1x.
reduces to x equals. The second product, what's going to cancel?
Y'all seen that.
The x minus 4s are going to cancel. What are we left with? Just a 4 over 1, which is just a 4, plus the third product. What's going to cancel?
None.
Nothing, because there's no fraction. We have a 5 sitting in front of those parentheses. What are we going to have to do here? It starts with a D. Multiply by distributing the 5 to give me what? Here.
5x.
Okay.
And then negative 20.
Okay. You know, this problem is not a bad first problem to solve. Unlike that, why did we have number 3? It's the first one to
I had
solve.
no idea.
Oh, okay. Well, I see something I can do. I see a 4 minus 20. That's a negative 16. So we have a negative 16 plus 5x. This is not quadratic. This is one of the nicer equations we're going to wind up with. If it's quadratic, we have to get it set equal to 0. What would you see here if it were quadratic? What makes an equation?
Just an x.
It's not just an x. It has to be an x square. There's no x square, so it's not quadratic. We can move all of that. Let's get all the x terms on the same side and then divide. I'm going to move the 5x over to the left by doing what?
I heard subtract.
So I'm going minus 5x minus 5x. 1x minus 5x gives us how many x's? 1 minus 5 is negative 4x equals a negative 16. Divide both sides by negative 4 to give us x equals, what are we getting here? Negative 16 divided by negative 4 gives me a positive 4. You know, I haven't even been switching back to my little recipe that I have here. It's just a vague general recipe.
It's not a real recipe.
It's not a real recipe because it's just we multiplied by the common denominator. That's what we did, the x minus 4, x minus 4, x minus 4. We cross-canceled to eliminate the fractions. We did that. We solved the equation. That's the third step. Now we have to make sure that any number we get doesn't give us a denominator of 0. We got a solution of x equals 4. Our denominator was x minus 4. If you plug that 4 into that denominator, what are you about to get? A 0. You plug that 4 into the denominator, you have to discard it because 4 gives a denominator equal to 0. All that effort, and it turns out there isn't a solution.
Actually, you found something.
Yeah,
you found
I found
that there's
something.
no solution.
Look, switch back to the problem. There is no problem. You could sit here for the rest of your life plugging in numbers for x on this problem number 4. And you will never make the left side equal the right side. Your children can take over once you die of old age, plugging in numbers, and your grandchildren. There is nothing you can plug in that will make the left side equal the right side there. So, and you're right, we did find something. You don't choose that option there.
I'm going to go ahead and get it wrong.
Oh,
Let's
okay.
see, 4.
You type in that
That's about
4.
it. Plug
I
in the
think
4.
they give you a helpful hint here. No, they don't.
Oh.
No, they don't. I thought they were going to say that gives a denominator of 0.
See, they tell you check by substituting into the initial formula. Oh, you don't have to do the plug into everything.
All you got to do is check that denominator. If the number gives you a denominator of 0, you have to discard it. Since we don't have another option, we
choose the empty set. Sometimes I'll say no solution. I think I like it saying no solution better, but that's not my choice.
Any questions there? Number 5.
Oh.
Okay, it's a 5 over x squared minus 54 over x is equal to 11.
Now the question I'm about to ask, students have a hard time with it because it's so easy. The answer is obvious. What value of x? You ask it since you have the knowledge.
What value of x would we have to discard? What value cannot possibly be a solution? What number would make the denominators equal 0? It should be obvious. 0. I'm going to make a little note right here somewhere. Once we're through solving this equation, if we get x equals 0, we're going to have to cross it out. But 0 is the only number that we can't use. If we solve this equation and we get 50 million, that's fine. If we solve this equation and get pi, that's fine. We just can't use the solution of 0. What do we need to multiply through by? What do we need to multiply through by to
get both? Oh, you marked out the x can't be 0.
Okay.
That was my mistake.
I know. Okay. What do we need to multiply through by in order to cancel out both denominators? I'll get us started. The common mistake is people say use x. The name is the least common denominator, so they use the least exponent. We have an x squared and an x to the first. People want to use x. I just put an x over 1,
This is a mistake.
x over 1, and an x.
Do both of those denominators cancel?
Look at this first product. Is this entire denominator going to cancel? No, because we only have one power of x up here. With that in mind, what should we have multiplied through by? You want every denominator to cancel, and if you just use x to the first, you're still going to be stuck with an x down there. So, suggestions, what should we use as our common denominator?
Not x, but
X squared.
Good.
If you have repeated factors, appearing as denominators, here we have an x and an x squared, you use the larger exponent on the factor. Repeated factors in denominators, use the larger exponent that appears on that denominator. So we're multiplying through by x squared. Okay. What's going to cancel in the first fraction? The x squared. We're left then with 5 over 1, which is just a 5 minus. You tell me what's going to cancel here. 1x cancels. We still have an x up there on top. X times 54 all over 1 reduces just to 54 times x. Cancel an x above and below. That left you an x up on top. What have we got on the right-hand side? What's going to cancel? Do we have a fraction to cancel anything here? So you're just stuck with an 11x squared. This thing is quadratic. I see that x squared. That means we're going to have to get it set equal to 0 and either use factoring or the quadratic formula. The instructions, if you look at number 5, it doesn't say solve the equation using the quadratic formula. That means this thing that I've got is factorable. If I can get it factored quickly, then that's what I'm going to do. If I don't see the factorization very quickly, then I'll go on to the quadratic formula, okay? But I see the factorization. Either way, we need this thing set equal to 0. Remember, I want the number in front of x squared to be positive. So with that in mind, remember what we were doing on Monday. Where will I get the 0? Well, am I going to get the 0 on the left or on the right? If I pick this term up and move it to the left, what's about to happen to that 11? It becomes negative. We don't want a negative leading coefficient. So I agree, we'll get the 0 on the left. We have a positive 11x squared. Let's move this x term over. What are we going to have then? Plus 54x. Move the constant term over. Minus 5. There's not that many possibilities here. Despite the 11 and the 54, there's not that many possibilities. What times what gives you 11? Yep, it's a prime number, so I'm going to just think of it as 1 times 11. What times what will give you a 5? Okay. We'll write our 2 sets of parentheses. The only possibility for the first, 1 times 11, so 1x times 11x. Oh, what do we know about the signs? The last sign's a minus. Okay, so it's a minus, so we're going to have one plus and one minus. I'll wait to put those in until a moment.
And hopefully it's clear to you why. It's not just you memorize my little things that I chant, second sign is plus, two of the first, second sign is minus, one of each sign. You're asking yourself, what type of numbers multiply to give a negative 5? Well, it's got to be a positive and a negative. So you can logic your way through.
Okay, 5. 1 times 5. I'm going to think through this as I place the 1 and the 5. What do we want the outer and inner to give us?
Something that equals
That 54 there? Well, if we put the 5 right here, that's 55. 1 times x, the outer is 1. I think that's the correct placement. That 55 and then a 1, that's going to give me 54 if I subtract. Where do I put the plus in order to get the positive 54x? Will I put the plus in front of the 5 or in front of the 1? In front of the 5. Remember, the bigger number gets the sign that's there in front. So we put the plus there, that means the minus is there. Y'all want to check the outer and inner to make sure that we factor this correctly? Here I'm checking. What's the outer product? Here's my scratch work.
Let's pull out the whole thing.
Okay, first, x times 11x is 11x squared. Outer. Okay, a minus 1x. Inner. Plus, okay. Last. Negative 1x plus 55x gives me a plus 54x. Is that what I needed? Yes, it is. So this is the correct factorization. We're not through with the problem, though. We still have to set each factor. Set the x plus 5 equal to 0. Set the 11x minus 1 equal to 0. This first equation says that x equals negative 5. The second one, what do I do first? Move the 1 over, so we have 11x equals a positive 1, and then divide by 11 to give us x equals 1 over 11. We multiplied through by the least common denominator. We canceled the fractions. We solved the equation. What's the last step? We got to cross out any solution that gives a denominator of 0. What's the only number y'all said that would give us a denominator of 0?
Look where the mouse is.
0.
Yeah,
So 0 is the only way you're going to get a denominator of 0. You have to plug in 0 for x. Did we get a 0 for our solutions? So both of these numbers are acceptable. You don't have to go all the way through and plug in and make sure the left side equals the right side. In a moment, when we get to radical equations, you're going to have to go through and manually make sure, plug it in your solution to make sure the left side equals the right side.
good. Give them something to look forward to.
But here, all you got to do is make sure that those solutions don't give you a denominator of 0.
Negative 5, comma, is that a positive 1 over 11?
Yes.
Okay.
Any questions there? Number 6.
These are some messy problems.
Oh, they're
okay?
not that messy.
Yeah, okay.
Wait, I don't know if I put it in wrong.
Uh-oh.
Let me see.
Oh, wait a minute. Your answers would not be my answers.
I
Oh,
think it was. I think it.
Let me see.
Oh, is it the same problem? Was
I
it
think
exactly the
this one
same?
is. This one's the same problem.
Well, sometimes that happens.
Yeah,
Yes.
but it's
Oh, what?
right here, but it's just super small and scattered.
Okay.
We cross out any solution that would give us a denominator of 0, but look at,
No, your numbers are different.
if you took
So
negative
that
5
one was the
squared, that's a
same.
positive 25.
So I
If you
just
plug in a
averaged it.
negative 5, that's a negative 5.
Is this
The only number that would give a denominator of 0 is 0 itself.
Has the 3 there.
If you try to plug in a
47.
0, you get 54 over 0, and we did not get
Oh, wait, here it is.
0
Okay, let me see.
as a solution.
3x squared.
Okay?
No, 3.
No, I think this is just different, and that's what I wrote. And I realized now I'm realizing it was different.
Oh, okay.
I'll solve it.
Number 6.
Thank y'all.
Oh, well,
Number
I'll look at it once class is over. If
Okay.
you need. Oh, look at number 6.
2x minus 7 all over x equal to x minus 4 over 4. Okay, let's switch
Right off.
to this.
What's the only number that would give us a denominator of 0? Don't say 3.
This denominator is never going to be 0. This denominator, as long as there's a denominator there, that denominator is going to be what?
3.
3. What would x have to be to give us a denominator in this one? In the first one. I mean, to give us a denominator of 0 in the first fraction. No, if x were 1, you'd have a denominator of 1.
Like the previous one, it's so obvious it's hard. 0 is the
Only number you could plug in for x that would make that denominator be 0. You don't want that denominator to be 0. So at the end, if we get x equals 0, we're going to have to cross it out. Here, this problem's different from the others because it's in the form fraction equals a fraction. Now, if you have two distinct denominators, neither of which can be factored, and neither of those denominators can be factored. If you have two distinct denominators, the least common denominator is the product of those denominators, x times 3. So if we're going to multiply by the least common denominator, it'd be 3x. But I don't want to do that. There's another method of solving proportions when you have one fraction equaling another fraction. And when we get to the cut point method of solving inequalities, it seems like we've run into these proportions more there. So I want to show you how I solve these proportions. There's another way, there's a little name to it that you may have seen when dealing with one fraction equals another fraction. What is that name? I'll get us started. The first word in the name is cross. Cross multiply. If you have, now your equation has to be in the form fraction equals fraction, and that's what we have here. So what we can do is we're going to multiply. Take the 2x minus 7 times 3. I'll write it like this. 3. Oh, that pen's no good. 3 times 2x minus 7 is equal to, you take the 2x minus 7 times the 3 is equal to, now you cross again, this numerator times that denominator. So you have an x times x minus 4. That second cross gave us the x times x minus 4. The first cross gave us the 3 times the 2x minus 7. We know what we're going to have to do to get rid of those parentheses. What are we going to have to do? Distribute. So you're going to get a 6x minus here. Okay. Equals distributing here. What are we going to get? x squared. Anything else? Minus 4x. Yes. It's quadratic. And the instructions don't say use the quadratic formula. Now, if we can't get it factored, if it takes us too long, then we'll use the quadratic formula. But the fact they don't say use the quadratic formula, that means it's factorable.
How did he know it was quadratic?
What did I see? There's something on this line that makes it quadratic. What is it?
The 6 and the 4 can be.
There's one little
X
thing,
squared.
the x squared, the
As soon as you
square
see
on
that-
the x. That's what makes it quadratic. That means get it set equal to 0 and try to factor or use the quadratic formula. It's this x squared right there that says that it's quadratic. Where do you think I'm going to get the 0? On the left side or on the right side? I'm going to get it on one of these. So, the left side. I don't want to pick up this x squared. I don't see a number there, so that's an assumed a value of positive 1. If I move it over to the left, what happens? Negative. You don't want a negative a value. That just leads to more reduction problems. So what I'm going to do, I'm going to get the 0 on the left. I think I'll use black. 0 equals, I have an x squared. I have that minus 4x. Let's move this 6x over. That'll become a minus 6x. And what else? Plus 21. Any questions there? I moved the 6x over. It became a minus 6x. I moved the minus 21 over. It became a plus 21. We can combine those terms. Negative 4x minus 6x. What's that going to give us? A negative 10x, I agree, plus 21.
Oh, I like this factoring.
Oh, I like the factoring too. It's a simple trinomial. X squared, there's only one possibility. What is it? 1 times 1. So we have 1x times 1x. We know something about the signs. Both. The last sign's a plus, so you're going to have 2 of the, no, 2 of the first signs. We're going to have to use some negatives down here, or else we'll never get that minus sign there. How do you use negatives to give you a positive product? Negative times negative. Remember, if the last sign's a plus, you use 2 of the first signs. If the last sign's a minus, you have 1 of each. It seems like the nice case doesn't appear as much as that minus case, where you have a plus and a minus, and you have to decide, where do I put the plus, where do I put the minus? But if that last sign's a plus, you know you're going to have 2 of those first signs. Now for 21, there's only 2 possibilities. 1 times 21, or, put that away. 1 times 21, or, so it's a simple trinomial. A simple trinomial, it's simple because you know the first terms automatically, but it's also simple because you can just look at this pair and pick out the pair you need. You use the pair that adds or subtracts to give you 10. In this case, they're adding. 3 plus 7 gives us a 10. To give us 3 and 7. Any questions there?
It doesn't matter where you put the last 2 numbers, right?
No, because the first terms are the same. X and X. Now, if this had been a 5x squared and you had a 5x and a 1x, then where you put the 3 and 7 would matter. We're not through yet. We need to ask ourselves, when are these factors equal to 0? When does x minus 3 equal 0? When does x minus 7 equal 0? X minus 3 equals 0 when x is equal to 3. You picked up that negative 3, moved it over, it became a positive 3. this thing here, x equals,
7. Positive.
and you'll notice I'm boxing these in. There's that fourth step. Make sure these don't give you a denominator of 0. But we've already said what number would give us a denominator of 0. The only x value that's unacceptable is 0. Did we get a 0?
No.
No? So 3 and 7 are perfectly fine solutions. Any questions there?
3, 7. What is 7?
Okay. What is it?
Let's see. Oh, better do this one.
Okay. This is number 7. Do you think I have room to do this on this page?
Oh, I don't know.
We're tree farmers in East Texas. The land our parents gave us is designated tree farming because we get a big tax break then. And we don't want to cut the timber. That's big business in East Texas. I suppose one day, if we're really hard up for money, we will, but
I'll feel sad. cutting
yeah,
those
after
trees.
so many, it hasn't been clear cut since 1978. Do you remember that?
And you're talking about these years way before any of y'all were born. Just like it dawned on me, y'all don't remember or weren't even born on 9/11.
Yeah.
Oh wow, I remember that day so clearly. Don't remember what I ate for breakfast. I'm joking. That was a bad joke. I know what I ate for breakfast, okay? But I sure
Well, back then we
remember
didn't eat
9/11.
breakfast.
No, I mean today. That was the joke.
Oh.
I don't remember my breakfast today, but I remember 9/11. That was a bad
That's
joke.
a bad joke.
Okay.
Okay, I'm waiting for y'all to tell me. Y'all should be able to tell me what I'm going to multiply by. Oh, I messed up on my writing, didn't I? Shoot.
What happened?
Okay.
Why don't you recopy the whole problem?
Okay.
He's now going to write the problem with
The
more
correct
spread
one.
out.
Well, I did spread out this
There.
thing.
But that 5.
I needed
I
to leave
noticed.
some space. This is giving y'all time to decide what you're going to multiply by.
I'll give you a hint. It's really
Don't.
not hard.
X minus 2.
Okay, the
minus two.
only denominator appearing is x minus 2, so that's what we're going to multiply by. You know something? Maybe I'm going to let y'all tell me how many times am I going to have to multiply by x minus 2. For distributing, that means every term has to be multiplied by x minus 2. How many total terms do we have? Remember, a fraction is a term by itself.
3.
So we have one term on the left, we have 2 terms on the right, so I agree, we're going to multiply by 3 terms. We're going to multiply 3 terms by x minus 2. X minus 2 over 1, x minus 2. I'm not going to put that over 1 because it's not even a fraction. You're trying to eliminate the fraction, so we're not going to create more. And right here, x minus 2 over 1. This canceling is not really that difficult. Once we start sticking in all those denominators, it really gets messy looking. But what's going to cancel here?
X minus 2.
That's why you wrote that x minus 2 here. You wanted to cancel it there. Leaving us with what?
Just 2x.
2x over 1 is just 2x equals, here, what's going to cancel?
Nothing.
Because there's no fraction. Well, we can distribute, though, to give us 5x minus 10, I agree, plus this last product. What's going to cancel? Oh, that's a square there.
2x.
The x minus 2 and the x minus 2 is going to cancel, leaving me what?
13x squared.
Just the 13x squared. Is this equation quadratic? Yes, because I see that x squared. So I need it set equal to 0. Where am I going to get the 0? Read my mind. Am I going to get the 0 on the left or on the right? On the left, because that's a positive 13x squared. I want that 13 to stay positive. There are all sorts of undesirable side effects if you have an a value that's negative. So we have 0 equals. That's a positive 13x squared. I think y'all are ready to combine the x terms like this.
Just write minus 2x.
I'll write a minus 2x and a minus 2x. What's that going to give me right here?
Plus 3x?
5x minus 2x gives me a plus 3x. What else do I have there on the right-hand side?
The negative 10.
Okay. So this should be factorable. If I can get it factored quickly, then we're going to go on to the quadratic formula. All right, my 2 sets of parentheses. What do I know about my signs? Is it nice like up here on number 6? On number 6, it was nice. That last sign was a plus, so we knew 2 minuses. We'd have to wonder if we were putting the minuses in the correct spot. We knew they were both minuses. What about here? The last sign's a minus, so what are we going to need? 1 plus and 1 minus. Well, is the plus going to go in the first parentheses or the second? I don't know. We'll have to wait. 13, well, that's sort of a large coefficient, but there's only one pair of integers that'll multiply together, positive integers that'll multiply together to give you 13. What is it?
1 and 13.
So we have a 1x times a 13x. Now for 10, there are 2 possibilities for 10. 1 times 10 or
2 times 5.
2 times 5. Playing it out in your head. Which one do you want to use? Most of the time I'd say go to the pair that's closest together. The 2 and the 5, but is that going to do it?
Maybe 1 and 10.
I think we're going to need the 1 and the 10. If you put the 2 and the 5, you get a 26 and a 5x. If you reverse it, you get a 65 and a 2x. And over near the 3x. So we're going to need a 1 and a 10. If I put the 10 there, 10 times 13x, what's that giving me? 130x? That's way off, isn't it? We better put the 1 there and the 10 there. So what's our outer product? X times 10x, that's 10x. What's the inner product? 13x. We need these things to subtract to give us what? 3x. I think we can do it. We would need a positive 3x. We need a positive 13 and a negative 10. Does that do it? Would that give us a positive 3x? So tell me where the plus goes. Will the plus go in the first parentheses or the second parentheses? The first parentheses and then the second parentheses. Now we have a negative 10x for the outer product and a positive 13x for the inner product. Any questions there? Set each factor equal to 0. The first solution, x equals negative 1, okay. The next solution, what will I do first? Okay, to give me a 13x equals a positive 10, and then divide by 13 to give me x equals 10 over 13. But you'll notice I didn't box those in. We need to make sure that they don't give a denominator of 0. My problem is so messed up. Look at the original problem on the my lab. Y'all can tell me. I didn't ask y'all this at the very beginning. What x value is unacceptable? There's only one x value that would give you a denominator of 0. What is it? I couldn't hear you. When does that x minus 2 equal 0? When x is a positive 2, x minus 2, we don't want that to be 0, so we don't want x to equal positive 2. Did we get a positive 2 as our answer?
No.
So both of these numbers are acceptable. For the fractions, you don't have to go through, plug in 1, and go through the original problem. All you have to do is make sure you don't.
Plugging a 10 over 13 in for this x.
That'd be a miss. That would be a
here.
miss. But you don't have to plug those in. Just make sure they don't give a denominator of 0. So both of those numbers are acceptable. Typing them in.
-1, comma, 10 over 13. Those are the rational equations. Starting with the next one.
Okay, this is still the same homework assignment, but remember the name of this section is Rational and Radical Equations. We've finished the rational equations part of the assignment. Now we're ready to look at radical equations. And when we say radical equations, we don't mean bizarre equations. We mean they can contain radical symbols like a square root symbol. We'll even see some cube root symbols. You may see a fourth root in this assignment. We'll see. These are radical equations. And that means they contain square root symbols, or you could have a cube root symbol. We're going to have some cube roots here. Cube roots get a bad rap. They're a lot easier than square roots, but people dislike them. Fourth roots, and so on. I don't think we're going to see anything other than square root, cube roots, or fourth roots. The last, it was the very beginning of the semester, wasn't it? The first class. I remember we came up with this little rule involving square roots. Hold on, let me switch back through here. Here's something that's scary. We've already used the first section of this notebook. I guess it's because I've done so much of the writing, and my writing is large, okay? When you're a penmanship award winner, multiple penmanship, I won multiple penmanship awards in my youth.
In elementary school.
In my youth, I won penmanship awards, Tony.
I don't know if they even do that anymore. Who can write the prettiest cursive
You're
writing?
just lessening my award. You're trying to, but it doesn't work. There's this hollow sound of jealousy, Tony, and it's not flattering. Okay.
Yeah, he got all the penmanship awards.
Do y'all remember this? We said if you have a square root times itself, then that's not the square root being squared, and the square undoes the impact of that square root. Do y'all remember this? We would say that something times itself, a square root times a square root, just left you with the radicand. That's going to be an important concept. And Tony, when we were writing this down the first time, I think one of us even said that concept's going to follow you throughout the semester. So,
you know what? It's so important. It's late, but I'm going to put a red star. That's a red star rule.
Okay.
Use it over
so
and over.
We said that if you had a square root of a and you squared it, that would just leave you with the radicand a. I'm using a for anything, okay? And if we're working with a cube root, just to remind you of what a cube root is, the cube root of 8, you're asking yourself, Instead of square root, you're asking yourself, what can I cube to give myself 8? What can I cube to give myself 8? What number? Cube means you write it twice. It's not
No,
one time,
twice.
I mean 3 times. It's not 1 times 1 times 1. What's the cube root of 8? 2? I agree. Because 2 times 2 is 4 times 2 gives you that 8.
A lot of times people incorrectly think 2 cubed is 6. No.
No, not my students. They don't think that, okay? My students don't think that. Okay? So here we have this other rule. Let's try to generalize the square root rule. If you take a cube root and you cube it, what is that going to leave you with? You take that cube root, which is 2, and cube it. It gives you back what you have under that radical for a for anything. In general, if you have an nth root, this little number here that's outside the radical is called the index. If you want to eliminate that radical, then that radical needs to be raised to whatever that power is there. You'll notice for square roots, we don't write the little 2 because by far those radicals, when you see a radical, most of the time it's a square root. Back before modern equation editors, the typing that little index was a hassle. So why do they not put a little 2 there? Because back in the olden days, they didn't want to have to try to type the 2. So, and as a result, square roots are the most common. But I do say it. I say a square root. You're right about that, Tony. I'm saying a cube root. We'll have a 4th root before the end of class. I think there's a 4th root in here. Although we removed one of these problems. Maybe it was the 4th root one. I don't think it was.
Wait, write out your strategy.
I'm going to write out a general strategy. I don't know that the general strategy that I wrote out for fractions really helped that much, okay? I don't know that it helped or not, but I just want to write out a general strategy to solve radical equations. To solve? No, before we do that, I'm going to write some examples. Suppose we had the square root of 7x and I squared it. If we had a square root of 7x, what would that reduce to? Just 7x. Whatever's underneath the radical. Suppose we had, let's say, the square root of, I'll make it an x plus 7 being squared. What's that going to reduce to? Remember, the square root of anything, when it's squared, it leaves us that anything. So what am I going to have here?
X plus 7.
Another x plus 7. Not a square. That square cancels out the square root. Just like there and there. So just x plus 7. It doesn't matter how messy it is underneath that radical. If you have a radical, suppose it was the square root of 5x minus 14, and we squared it. What would that leave us with? 5x minus 14, yes. As long as all of the stuff is under the radical, then when you square it, the radical disappears from the equation. Suppose not all of the stuff is under the radical. Suppose we had, look at this one, compare it to that this example right here, okay? I have a square root of x, and I have a plus 7 stuck on. Notice I'm going to close off that little square root there, and I wanted to square it. The plus 7 is no longer under the radical. I'm trying to make a point here, so just bear with me. The plus 7 is not under the radical. If everything's under the radical, the square root, when you square it, great, you're left with the radicand. But here there's a sum that we're trying to square. How do we square a sum? You're not just trying to square a radical, you're trying to square a sum. And this is another concept from the very beginning of the semester that we said you would have to, that it would follow you through this semester. I remember squaring a sum on the first day. I think maybe it was the second day. The second day with eyes. You're right. Okay. So let me find that. I remember squaring a sum here somewhere. Let's see. Look at this number 9. We had a sum that we had to square. We couldn't just square the -3 and square the 7i. To square a sum or difference, what do we have to do? Write it twice and FOIL it out. Just because you square a radical doesn't mean you're going to get rid of the radical. In some cases, you're going to get something a lot worse than what you started with. Write that twice. The square root of x plus 7 times the square root of x plus 7. Notice the plus 7s are not under the square root. First, the square root of x times the square root of x. The square root of x times the square root of x is the square root of x squared, so that reduces just to x. Great, we got rid of that radical in the first product. What about the second product? What's the outer product going to be? The square root of x times 7 gives me a positive 7 times the square root of x. Apply that logic to the inner product. What are we getting here? Look at the inner product. I'm not going to say it. Y'all tell me, what will that inner product be?
7 square root of x.
So the same thing we just had. 7 square root of x. Last, 7 times 7. That's easy. I'll do it for you. 49. So we started off with the square root. We squared it. What's that going to give us? We have an x. 7 square roots of x plus 7 square roots of x. How many square roots of x are we going to have there?
2.
No. 7 plus 7. Remember when adding radicals, we said you had to have like radical terms.
On day 1.
On day 1, we said to add radicals, you need like radical terms. And, right here. Once you have the like radical terms, you keep the radical term, you add or subtract, in this case, add their coefficients, and that's what I'm about to do here. 7 plus 7 gives me 14 square roots of x. I think we squared something. We thought we would get rid of the radical, but did we? We got something worse than what we started with. We started off just with the square root of x and a plus 7.
I have a
But-
question.
Yes.
When you distribute the x to the x, why is it just x?
The square root of x times the square root of x is the square root of x squared. And what did I say? A
That's
square
just-
root of anything, when it's squared, that
it.
square
Oh, okay, yes. You just-
cancels out the square root,
Okay.
leaving us just the thing under the radical. There's a lot to think about here. There's a lot to think about and a lot to remember. The whole point of this last example was to show you that just squaring a square root doesn't eliminate the square root. As a matter of fact, you may get something worse than what you started off with. So, the moral of this story, note, before, whatever you do to one side, we're going to be working with equations. So whatever you do to one side of the equation to maintain the equality, you got to do to the other side. We know that. So If you're going to square both sides of an equation to get rid of a square root, you better make sure that the square root is isolated. You don't want a radical with something added or subtracted to it. You have to move that stuff to the other side. I'm going to say before raising both sides of an equation, to a power, if it's a square root, you'll square both sides. If it's a cube root, you'll cube both sides. If it's a fourth root, you'll raise both sides to the fourth power. Before raising both sides of an equation to a power, you need to have a radical term isolated. I'll say you must first, I say isolate a radical term because you may have more than one radical symbol, but you must first isolate. If you have more than one of the radicals, one radical, you got to isolate one of those radicals. I'll say isolate a radical term. Otherwise, I'm going to put an exclamation point. That's important. That's important because otherwise you're going to wind up raising both sides to power and get messier stuff. Wind up with an equation that's a lot worse than what you started with. So, here we've just been talking in generalizations and stuff, not really looking at any radical equations. Just some general properties involving radicals. The important property being that whatever type of radical you have, that's what you raise both sides to. And before you start raising both sides to a power, you have to isolate a radical. Don't want me to write out a general pattern that a procedure that I'll follow to solve radical equations, or do you just want me to do one? Okay, I'm going to write out a general pattern. A general procedure to solve a radical equation. To solve a radical equation, first thing you have to do is make sure that one of the radicals is by itself. You don't have a radical plus something. You have at least one radical by itself with nothing added to it or subtracted from it. So the first thing I'll say is, if necessary, isolate a radical. If necessary, sometimes it'll already be set up the way you want it. Isolate a radical term. And then 2, raise both sides to the power of the index on the radical. If it's a square root, you'll square both sides. If it's a cube root, you'll cube both sides. That's what I'm trying to say here. Raise both sides to the power of the index on the radical.
So square roots, cube roots, so forth.
If you do this correctly, you should isolate that radical term that was
you'll be eliminating the radical term that you isolate.
Yes, okay. So I'll say
cancel out a radical term.
I guess I'll just say it like that. Cancel out the radical term and simplify. Now, if you still have a radical term remaining, you then have to repeat this process, okay? Isolate the remaining radical, square both sides, eliminate the radical. So I guess on step 4, I'm going to write it in red because hopefully we don't have to do this very much. If necessary, repeat process. To isolate the remaining, I'll say any remaining radicals, any remaining radicals. That's in red because we're hoping that once we go through one round of squaring, hopefully there won't be any radicals remaining. Fifth and final step. Not fifth and final step. I guess there's more than there's two more. We have to solve the equation. And here's the problem. Sixth step. You're going to have to manually plug your answers in to the radicals and verify that the left side of the original problem equals the right side for radicals with even indices. I'll say
for even roots.
For even roots, you got to check your answers. You don't always have to check your answers. Cube root 3, is 3 an even number or an odd number? Odd, you don't have to check for cube roots. That's why I say that cube roots get a bad rap. From a calculus point of view, cube roots are great also, okay? From an algebraic point of view, people don't like them just because they don't work with them that often. But cube roots don't create imaginary numbers. What makes imaginary numbers? Square roots. The cube root of, say,
you're going to get logged out.
The cube root of -1 is a -1. Negative numbers under odd indices roots, those are fine. But with that in mind, maybe we better mention this last step. We're going to a little more. I want to show you something. Just because we square both sides of an equation doesn't mean that what we're saying originally is true. I think y'all will agree that as long as I have those squares, that's a true statement, isn't it? What's -5 times -5? That's 25, isn't it? What about here? 25? That's a true statement. As long as you have the even exponent, it's a true statement. Suppose we drop the even exponents. Let's go back to the original statement. Is this accurate? -5 is equal to 5. When you're squaring both sides, you may take something that's negative and square it and make it positive. That's fine. But when you go back to the original problem, that's going to create errors. So it's those even exponents where we're going to have to check. So let's look at number 8. We have the square, no, x minus the square root of 7 minus 6x is equal to 0. Okay, switch over to the paper.
Okay.
The first step. Well, first of all, what power am I going to have to raise both sides to? Am I going to cube both sides, square both sides? What sort of a radical do I have? What sort of a radical is this? Is it a cube root?
Okay, it's a square root. You're going to square both sides. So let's get going.
Okay, so have we, the radical term needs to be isolated. Is it isolated? Is it by itself on one side of the equation? No. I can think of one way to easily isolate that radical term. What could I do? Because look at what we have here with it. We have a minus in front and we have that x. What could we do? We want that radical by itself on one side. Move the radical term to the other side. When we do that, we'll have x equals, we'll pick this up and move it over. All that's going to do is change the sign in front. It doesn't change what's underneath that radical. You just have a positive square root of 7 minus 6x. Any questions on my logic there? I'm trying to isolate the radical. I don't want that anything. I don't want that anything added to or subtracted from that radical term. So I've done the first step. I isolated the radical term. This is a square root, so we have to raise both sides to a power. What power will I use? Square. It's a square root, so we're going to use square. So the left side is just an x squared equals, what about on the right side? What's the right side going to reduce to?
7 minus 6x.
Okay, we've eliminated the radical term. We've gone through, isolate the radical, raise both sides to the power, cancel out the radical term and simplify. That's what we've just done there. Now we're ready to solve this equation. This equation is quadratic. That means we need to get it set equal to 0. Will we get the 0 on the left side or on the right side? Or better yet, I guess the better question is, where will I get the 0? On the left side or on the right side? On the right side, I don't want to pick up that x squared and move it to the right, because then that positive 1x squared would become a negative 1. So we have a positive 1x squared. Move those terms over to give me a plus 6x minus 7 is equal to 0. I'll write my two sets of parentheses. X squared, what times what will give me x squared? X times x, 1x times 1x. What do we know about the signs? One positive and one negative. The last sign's a plus. Since those first terms are x's, I'll just put a plus and a minus. And then what times what will give us 7? 7's a prime number. That's pretty nice. 7 times 1. Play it out in your head. What should we put here? We want to get back a positive 6x. Should I put the 1 here or the 7 here? Which one's going to go right there? We need a, with the plus. We want a plus 6x. A 1. I think we're going to need a plus 7 and a minus 1. Remember, the bigger number goes to the thing, has that sign there. 7 times 1 for a simple trinomial. For a simple trinomial, let's check the outer and inner and make sure that we've got it factored correctly. The outer product, x times negative 1, is a negative 1x. What's the inner product?
Positive 7.
Positive 7 times x is a positive 7x. Negative 1 plus 7 gives me a positive 6x. Is that what we needed?
Yes.
Yes. Set each factor equal to 0 to give us x equals negative 7, or x equals positive 1. We've gone through now the fifth step. We solved the equation. Now we have to check. We've raised both sides to an even power. 2 is an even power. That's why I said cube roots are nicer. 3 is an odd power. You don't have to go through this last checking stage. My advice to you, when you're checking, check at the stage where the radical was isolated. I shouldn't have stuck those squares on there. What did we have when the radical was isolated? We moved that over. It was x equals the square root of 7 minus 6x. Isn't that what we had before we squared both sides? My advice to you, for ease of checking, use the isolated radical form. And you'll see why I'm going to do that. What number do you think will be easier to plug in, -7 or +1? Surely +1 is easier, right? Let's do this one first. Plugging in 1, we're going to get a 1 equals the square root of 7 minus 6 times 1. What's 6 times 1? 6. 7 minus 6 is 1. Does the square root of 1 equal 1? Is that a true statement? What's the square root of 1? 1 equals 1? Yes. So 1 is an acceptable solution. Now let's plug in -7. I'm going to plug in -7 for x. So I'll have -7 equals the square root. Wait a minute. I can stop right there. This cannot possibly check. If you use the isolated form the way I said to do, I don't see a sign in front of this radical here. What sign do you assume you have? If you don't see a positive or negative, what sign do you assume you have? A positive? Can a positive equal a negative? Can a positive quantity equal -7? No. Right there, that -7 can't work. We don't even have to plug it in the rest of the way and verify it. By using the isolated format, when checking, if your x is a negative value, you can see pretty quickly that it isn't going to work. Sometimes the negative values will work, but in this case they don't.
But if you
Only
actually
solution
went
we
through,
get.
they would get a 7 plus 42, which is 49.
And you get -7 equals +7, which is not true.
Goes back to what you were talking about right there. Except it's sevens instead
You
of
see
pi.
the way those even exponents, they take negative things and make them positive, so it looks like it's a true statement. But without that even exponent, -5 doesn't equal 7.
It's like
That's exactly
-7
just like
doesn't equal-
-7. -7 doesn't equal +7.
So only one answer. Let me type that in. Just one?
Yes.
Oh, okay. That was
We
one.
remove number 9.
So we'll go on to number 10. Oh, this is another good one.
Number 10.
Another square root.
You know something? We've been going an hour 33. I think it's time to switch over.
So this is another square root equation. Let me write it down. So are we going to have to check our answer on this one?
Yes.
Yes, because it's a square root. That little index there, you don't see one, but you pronounce this as a square root. 2 is even, so you're going to have to check your answers at the end. Question.
The last answer was 1, right?
Just
That-
one.
Just one. Just one.
Oh.
Oh, wait. The last answer was just the one. You crossed out the...
-7.
Okay, did you write that down?
Well, the first thing we're going to need to do is isolate the radical term. And a square root of 6x. So to get that by itself, I'm not going to move it over because then it's going to pick up a negative in front of that square root.
They can tell you what we're going to do. What's he going to do here? I guess he's going to do
I'm going to do it. So we have square root of 6x equals, what am I going to have on the right side? A positive
X.
x.
And I couldn't hear the last one?
Okay, good. Now, since it's an even root, it's a square root, we're going to have to check it. The next one we do will be a cube root, we won't have to check it. But since we're going to have to check it, this is what I'm going to plug into.
Put a little star there beside that. That's what you're going to use to check.
Use to check. But I'm now going to recopy it. And we're going to get rid of that square root. What do I have to do to both sides to get rid of that square root? Raise it to what power?
2.
2.
And now
don't
you begin
say
to see what
x squared plus 144, a sum or difference being squared. By isolating the radical, you're not going to have to FOIL out something with the radical, so that's a plus, but you're still going to have to FOIL out that x minus 12 times x minus 12.
But that would be easier than FOILing out, well,
that'd really be
anything with the radical. So here the square root and the square cancel, leaving us just a 6x. Now the right-hand side, that's going to be a little messy. I'm going to think of that x minus 12 squared as x minus 12 times x minus 12 and FOIL that out. What are we getting when we start FOILing this out? It'd be x squared. Okay, I'm FOILing out x minus 12 squared. X minus 12 times x minus 12. First, x squared. Then outer would be a minus 12x.
What's the inner product going to be?
Negative 12 times x.
Another, okay. Last.
Negative 12 times negative 12 is a positive 144. I'm going to go ahead and combine the negative 12x minus 12x. Negative 12 plus negative 12, that's a negative 24x. And we have a quadratic equation, don't we? So we need a 0 on one side.
Where are we going to get the 0? On the left side or on the right side? The left side.
I'll just do this. I'm moving that 6x over. So I have a 0 on the left, and then x squared, negative 24x minus 6x, that's a minus 30x, plus 144. Oh gosh. Well, this will factor. If you want to use the quadratic formula, okay, but let's see. It's going to be it's not that bad because it's a simple trinomial. It'll just be x and x.
What do we know about the signs? We know something nice. They're both going to be minuses, so we have x minus, x minus.
One pair of numbers stands out for me. 12 times 12 is 24. But those won't add together to give a 30. So let me think. 1 times 144, 2 times 72, 3 still too big. Right?
So 144, how about dividing it by 6?
What's 144?
There it is. 6 times 24. Remember, you need the pair since it's a simple trinomial. Choose the pair that adds together to give you 30. I think it's 6 times 24.
Now, do y'all agree with the factoring? Set each factor to 0 and isolate the x. So x minus 6 equals 0 means x equals 6.
Is your speaker working?
And the other one,
Yeah.
let me try it like that. If I go x minus 24 is 0, we get x equals 24.
Some people get the idea if the solutions are positive, they don't have to cross them out. No, we don't know that. You may cross out a positive number. You may have to discard a positive number. But let's see.
Let's come over here.
There's the form that we're checking on.
Okay, so I'm about to take this 6 and put it in place of this x and this x. So be careful. 6 times 6, what number do we have under that square root? If I plug a 6 in for this x, is that going to be a
36
36?
equals,
Now here's where it gets interesting. Replacing this x with 6, we have 6 minus 12. Is this going to, remember this symbol here, the square root symbol means principal or positive square root. So the positive square root of 36 is 6.
positive 6.
Excuse me, it's positive 6.
I just meant write the little plus.
Oh, okay.
Because what are we going to have over here?
Is this going to check?
That's negative 6. It's the way when we were squaring both sides, somewhere along the way we squared a negative quantity without realizing it and made it into a positive quantity. That's why we got that solution that doesn't check. The solution that doesn't check is called an extraneous solution. Now,
let's plug in the 24 now.
Here's something you may want to remember. It is extremely difficult to rig a square root equation where you get two solutions that don't check. If we know 6 doesn't check, I'd bet large sums of money that the other number is going to check. If I were taking a test and running out of time, 6 didn't check, I'd assume 24 did check and go on. But let's go ahead and check it. Plug in 24, Tony.
So we have 6 times 24.
That's 144.
That's 144. If you doubt me, plug it into your calculator. And then we have 24 minus 12. Is that going to check? The 24 minus 12 is 12. This symbol, once again, means positive. Is this one checking? The positive square root of 144, isn't that 12 also? That one checks. 24 checks. 6 doesn't check.
So you may have some positive solutions showing up that you have to cross out. Those solutions that you cross out are called extraneous solutions.
Type in that.
Oh, yeah. I'm just winded from. Okay.
24.
24. Any questions there? Number 11.
Oh, when I see number 11, I think, oh,
good.
It's a cube root. You don't have to do any of that checking.
That 3 there, that little index is an odd number. So at the end, you don't have to check. You can if you want to, but they're going to check, okay? Cube roots do not generate extraneous solutions. It's the even index roots, square roots, fourth roots, sixth roots where you have to check. You got it written down?
Okay.
Okay, there's only one correct next step. What is it? There's only one correct
I heard
first
someone
step.
say 6. Yes.
Okay, you're isolating the radical. You need that radical term by itself.
So we have cube root of 2x plus 9 equals, move that 2 over, get a 6. Now, what exponent will I raise both sides to? And am I going to have to do any foiling on this one? Say no.
What power is he about to write in red up there?
A
3. Okay, good.
Mm-hmm. 3. 3. And on the left-hand side, you're just cubing a cube root. So all of that cancels, leaving the 2x plus 9. Oh, don't say 18. 6 times 6 times 6.
216?
Yeah, 6 times 6 is 36 times 6, 216.
Hey, are we going to have to factor here? Do we need to get it set equal to 0? Is this quadratic? It's not quadratic. All we got to do is get that x by itself. What will he do next? Minus 9, okay.
So we have 2x equals 216 minus 9, 207.
207.
And now what do I do?
Divided by 2.
Divide by 2.
And look at what he's about to do now.
I'll circle it.
There's the answer.
No checking or anything. These cube odd roots are really nice. Okay. So 207 over 2.
Okay, let's punch that in. 207 over 2.
Uh-oh. What did I do wrong?
I wrote it.
Oh, wait. Did I miscopy the problem?
Oh, my goodness.
Oh, my gosh.
Oh, Tony.
Oh,
well,
wow.
okay. It's okay. We don't have to redo it. It's still the same. Well, we don't have to write it. We don't get graded, okay?
I know, but it should be, if it were equal 9,
then that would be a 7. And 7
cubed is...
Y'all don't write this down, okay? It's just
pretend this is the problem.
343.
Okay, so 3. We'd have a 343 right
minus
here.
-9.
Minus
so
9.
it'd be 334. Oh, it would have worked out nicer.
Oh, wow. So we're going to wind up with a 100, what is that?
167? Oh, I wasn't expecting
But again,
that.
Y'all don't need to write that down because, you know, this is a better example as a fraction as the answer. Okay, that's what I wanted to do. So,
any question? Let me switch back. Don't look at what we typed there. The answer for the, mark off all that gibberish. Oh yeah, that's better. Okay.
Okay, so.
Any questions there?
But it was actually a 9.
We should have
which would have changed the 7 to a 6.
No, it would have changed the 6 to 7.
7 cubed is 343. Subtract the 9. Oh, wow, I can't believe we made that mess. Oh, gosh.
Under normal circumstances, we would do it again with the correct number, but I think y'all are wanting to lead badly, and we still have some important problems to do, like number 12.
Oh,
Now, this cube root problem won't be as painless as the previous one, but we still aren't going to have to check this because it's a cube root. Hey, there are 2 cube roots. Y'all be thinking about this. We need to isolate one of those cube roots. I see a smart way to get, if we do it correctly, we'll get both cube roots isolated in one step.
And not have any negatives.
I better check this.
On the 4.
Minus. Yeah, okay. So what do y'all think?
Only one correct first step.
Only one sensible and correct first step. We need to isolate a radical, and we don't have a radical isolated. They're both on the same side. What's the intelligent thing to do here?
Move the first one over to the right or move the second one?
The
Oh,
second one.
The
The
second
second
one.
one.
If you move the first one, that radical is no longer isolated. You'd have a negative there, okay? Moving the second one, the minus changes to a positive, so we're now isolating both radicals in a single step.
and now since it's a cube root, I'm going to cube both sides. Do y'all see how nice this works out? It actually is easier than if there'd only been one radical. Am I correct about that? I was saying
Because
that?
otherwise you would pick up a 216x cube.
Yeah.
So, yeah.
See here, all that's going to happen is I'm just canceling out those cube roots. So we have 5x squared plus 5x minus 4 equals 6x. Oh, well, unlike the previous one, this one's quadratic, so we need a 0. And then
Where are we going to
factor-
get the 0? Left side or right side?
Right side.
Mhm. Yeah.
Move
Move that
over.
6x over. So we have 5x
Square.
squared. Then 5x minus 6x is a minus 1x. Minus 4 equals 0. Going back to the previous problem, if y'all ever notice I miscopied a problem, it's okay just to yell out. You know, you have to yell it in my good ear. I'm joking about that, sort of, but still. Oh gosh. Well, second sign is minus, so we're going to have 1 plus and 1 minus. When I look at this, I think, oh darn, it's not just x squared. It has that 1 in front. So it's going to,
No, it has a 5 in
a
it.
5 in front of it. So it's going to have to be a 1 times 5. So I'll go 1x and 5x.
What do we know about the signs inside the parentheses?
One's positive.
Yeah, one's positive and one's negative.
Mhm.
Now for 4, there's 2 possibilities. What are they?
1 times 4 and 2 times 2.
Okay,
Normally I'd try 2 and 2. I don't
but
think
that's not going
gonna
to work. 2 and 2 will give you a 10 and a 2. There's no way that's going to give you back a subtract to give you a 1. So the only other possibility is a 1 and a 4, so try that. So the outer product is a 4x.
Okay, so if we start foiling it out, we have a 5x squared and then a 4x.
What's the inner product? A 5x.
5.
Now,
And we need these numbers to subtract to give us, what is that coefficient on x? A negative 1?
Mhm.
Okay, we need a negative 1x. How do we need to place the signs? Where should you put the plus? Where should you put the negative?
The negative's in front of the 1.
Okay,
Okay, so the 5 should be negative, the 4 positive. To get the 5 negative, that means put a minus
in front of the 1 and then the plus.
plus. Y'all follow that? There's so much going on. You go step by step by step.
And you can't forget anything that you've already learned.
Okay, so we have x minus 1 is 0. Move the 1 over. Can I circle the 1 or do I need to check it?
Wait, what power did we put up here?
If it's an odd
num-
root, you don't have to check it.
You can if you want to.
But you're making it harder than it needs to be. And what about this, especially over here? You'll be glad you don't have to check this one. When you set the 5x plus 4 to 0, move the 4 over and divide by 5. Aren't you glad you don't have to check this one? You only have to check the odd root.
Even root.
Even roots. You don't have to check the odd. I should make that statement. Now, if you're a view and example type of person, they say check it always.
It's just not necessary.
But I'm
For
going
an
to
odd
tell you,
index.
it's going to be a little messy plugging a -4/5 in for every one of these x's.
Even if you use the isolated form,
Yeah.
it's still going to be messy.
So 1 and -4/5. Cube roots are definitely, cube root equations, easier to work with than those square root equations.
1 and
Plus you don't have to
-4
worry about
over
checking.
5.
1, okay. And let's
Look at number 14.
One last problem.
Look at this problem.
Does number 14 look different from all the others? Let me ask the question, why? That big messy,
Those
fractions,
fractions.
the 1
That
over
1 over
3. Let me write it down, and then I'm going to tell y'all that this problem is exactly like the one we just did.
Yeah, number 12 wasn't.
Actually, it's easier than the one we just did. But at first glance, when you look at it, you think it doesn't look anything like.
It doesn't look like a radical equation. Why
What's
is that
missing here?
Maybe some radical symbols. I see exponents. I see binomials in the parentheses, but I don't see any radicals.
Here's something that's going to follow us the rest of the semester.
Once we get to logarithms, it's really going to be important.
Another rule that has a red star by it. It's going to follow us all semester long. I'm defining what these little fractional exponents mean. In general, a 1/2 exponent is the same thing as a square root. A 1/3 exponent is a cube root. I'm wondering if y'all could figure out the pattern.
A 1/4 exponent is the same thing as what type of radical? A 4th root. And in general,
if you have a 1 over n exponent, so if you had a 1 over 10 exponent, or a 1 over 20, that would be a
the nth root.
root.
So with that in mind, let's rewrite number 14 using radicals. I want to try to make number 14 look like the problem we just did.
If we replace these red 1/3 with the red cube root, it's actually going to look easier than the one we just did. The most basic problem-solving technique. If you know how to do one type of problem, speak going on. Okay. If you know how to do one type of problem, and we know how to do cube root minus cube root, that's not that bad, even if there's exponents, like a square in it. Well, here we've rewritten this one to be cube root minus cube root.
There's only one correct next step. What is it?
Now that we've
Before you raise both sides to a power, you must first, isolate a radical. Move that second radical is the smart thing to do, because when you do that, what's going to happen to this minus? It becomes a positive. Okay.
So we have the cube root of 2x plus 5. I'm moving that over, so it'll just be equals cube root of 7x minus 1. I bet y'all don't even need me to finish this one up, but I'm going to. Hopefully you see.
What's he going to do now?
Very simple.
Cube both sides. Okay.
I like those ones that we can write cube root equals cube root. So that cancels. That
cancels. I wouldn't be surprised if there's a problem like this
On the first
on
test.
the practice test and on the test.
Mm-hmm. I'd be surprised if there weren't. Okay, go ahead.
We have just a 2x plus 5 on the left, a 7x minus 1 on the right.
Are we going to have to get this set equal to 0 and factor? Is this thing quadratic? No, it's not quadratic. There's no x squares. Just collect all the x's on one side, isolate those x's, and divide. So
I'm going to move the stuff around so I get as few negatives as possible. I want to isolate the x. I'm wondering if y'all can follow my little arrows, what I'm going to do here. Arrow like that. And like that. What am I saying I'm going to do? Now, 7x minus 2x. That's giving me a 5x on the right. And what am I going to have over here on the left? 5 plus 1
not
is
minus 1, plus
1. Okay, I'm adding 1 to both sides. Heck, I could have done it like that and subtracting 2x. That's where I got the 5x. And what's going to be over here when I add 1? 6. Are we almost ready to...
Type in the answer.
Yeah, what's one more step I got to do?
Divide by 5.
Divide by 5. Over 5, over 5. X is by itself. Do I need to check it? No, it's a cube root.
That's
Odd
an
root.
even number. You know something? Draw a little arrow there with that little 3 and write out even. I mean even. Odd. That's an odd number.
Odd.
So don't
check. Okay. So 6 over 5.
I'm waiting. I think some students are still writing.
Oh, okay.
Okay.
Normally we do a better
5.
job of preparing them, telling them this is one of the longest assignments this semester.
I told him that.
Oh,
I think I said that the last time on Monday.
Now, on the next problem, you're going to start
Look at number
noticing
15.
that is that the same thing we've been doing, square root and
The quadratic formula.
is it rational and radical? No, it's just reviewing the past assignment. Use the quadratic formula. You'll start noticing when we think, oh, we don't have enough. I like 15 problems. And so I added that one just to get it up to 15. Originally I had 14, but I've marked out 2 of them. But someone had already clicked on it, so it wouldn't let me actually delete it. But it will let us give you credit for problems 3 and 9, and then just don't do them. So
Okay, now if your head's spinning now and stuff, just think about this. We knocked out the 2 hardest problems. 3 and 9 were the 2 hardest problems in the assignment. So
I can't believe we ever had 3 and 9.
we always did.
Look at the old videos if you want to see the 2 we marked out. Okay? And then you'll be grateful. I'm always looking, I'm an optimist. I think things could be worse. Some people say I'm a pessimist. But
These videos are on YouTube or on the
Okay.
emails.
Okay,
Tim,
hold
why
on.
don't you go
First
ahead
of
and
all, I'm going to stop